So I'm Sean Williams, and so on one hand, this talk is about the programming language that my friend John and I are developing. But one caveat is this talk will not actually be about that programming language. This is a conceptual talk. And the other caveat is this talk isn't entirely about parallelism. It's only even somewhat about parallelism. It's actually started out being about safety more than anything else. So I'd probably start by, trying to connect that title a little bit. So first off, if you don't know, a race condition is a situation where the ordering of things is important, but it's also ambiguous. Something that I really want to impress on everyone about this is important is sort of the key word. Nothing is important to a computer. We're the ones who think things are important. And the entire act of programming is focused around attempting to impart our intent or force the computer to do what we want it to do. The computer will always do something, but oftentimes not the right thing. But again, the right thing is what we have in mind. And because of that, race conditions are a modeling problem, not really much of a technical problem per se. And I often find that when dealing with modeling problems, it's often easier to deal in systems that have a little less pretense than computer science and math. So instead, I'm going to talk about a card game called Magic the Gathering that my brother and I played a long, long time ago. So the thing that you have to know about Magic and Magic cards are that they have types, which are indicated on this central line. They can have any number of types, but they must have at least one. This one has type creature. Also, they have abilities, which is the Roman, the non-italics text in the bottom box. And everything about the Magic card can be changed in flight. The card represents the initial state of a Magic card. But within the game, the state can change fairly radically. So the following situation did actually come up when my brother and I played. And I thought it was hilarious, but it ended up leading to a pretty complete retread of the rules system. So the left card is called Humility. It's an enchantment, and it says, all creatures lose all abilities and become 1/1, which is their combat effectiveness. The right card, Opalescence, says, each other enchantment gains the creature type, and its power compass is set to its top, which is in the top right corner. Now, you probably recognize that there's a race condition here. Opalescence turns Humility into a creature, so it becomes a creature and an enchantment simultaneously. At which point, Humility will attempt to remove its abilities, including its ability to remove its own ability. So, how did Magic solve this? They didn't, after Urza's Destiny here, they didn't say, well, I guess that's it. Let's pack it up and make another game. Although, maybe they should have. No, instead, they recognized something really important about this situation. They phrased this text in a continuous fashion. These seem to be things that are just always happening. They're background text. But really, they're actually events. Humility, as I said, Humility becomes a creature. It is undergoing a discrete change. And the discrete events are occurring in discrete time. And in fact, that was the solution that Wizards of the Coast came up with. So the game has a discrete temporal resolution, and it works like this. The bulk of the game, without going into a lot of detail, consists of 2 or more players alternating, taking turns taking actions. And in between players declaring actions, you go through this really ridiculous process where all effects are removed from all cards, and then they get immediately reapplied, and then the game stays inspected for changes. Also, when effects are removed, or between the removal and reapplication, the game state is snapshotted. The other thing that they did is they doubled down on continuous effects as a game term being alive, and made them discrete effects that are simply constantly reapplied in a particular order. So this was the radical rules change. It was bureaucratizing the rules. So now, the entire official rulebook for the game is written like this, in section, subsection, sentence style, which they can then reference in that format if you look at the official card text. But more importantly, the continuous effects get reapplied in a particular order. And if you follow this through, what you will find out is that humility becomes a creature enchantment with no abilities. And if there's a second opalescence in play, then all of them will be creature enchantments with no abilities. And the power and toughness depends on the order in which they enter play, which is a rather bad oversight on their part. So race conditions fundamentally occur because of discretization of continuous systems. So then the question becomes, why don't we deal in continuous systems? Well, probably the most compelling reason is that in general continuous systems lack a representation. So you might ask, this is a spectrograph, which is a common visualization sound. So you might ask, well, aren't I showing a representation of a continuous system in this image? And the answer is no. I'm showing a discretization of a continuous system. In fact, if we consider this more broadly, the main thing that we can actually do is define processes that define continuous systems. But in order to really do very much with them, if they're at all complicated, we have to begin by discretizing them, as demonstrated by this fractal, which is an image, noteworthy, an image in a discrete image space. And there is no continuous way of visualizing a fractal, even though they are continuously defined. Now, to try to veer this back to functional programming in computer science, let's consider an odd math problem. Select two random real numbers between 0 and 1. In fact, the probability that you pick the same number twice is 0. Not approximately 0 or very low or infinitesimal, actually 0. And the reason is that the probability of selecting any number from x options is 1 on x. And there are an infinite number of reals between 0 and 1. Therefore, the probability is the limit as x approaches infinity of 1 on x, which is 0. Now, this seems strange. Does this mean that we can't actually select random numbers? And the answer is actually kind of yes. The problem is that I asked about real numbers which have infinite resolution. So how do you actually select a number with infinite resolution? Really, you can't. We could define algorithms for, if not random, at least pseudo-random numbers, but they're always finite. An algorithm that selects an actual real number would be non-terminating, so you're on. And in that sense, the question itself lacks representation. There's no way that we can actually carry it forward into reality. It's kind of a pointless exercise. Now, here's where things become a little controversial. A pure expression, that's the expression of referential transparency, means that you can replace a pure expression with its result without affecting the program. Now, this is also an odd thing to say, because what does it mean to not affect the program? This is another one of these situations where we need a time machine to figure it out, because the state space of the program is incredibly large, and pure programs actually run on computers which have to use stacks and heaps in order to execute them. And it sort of boils down to that old philosophical saw about whether someone can ever step in the same river twice. In that case, when you're talking about whether you can walk in a river or even define a river, it's sort of a non-issue because a river is not exactly a formal thing. It's a convenience that we use to discuss, the way that our lives are going or, where you live. But this is supposed to be a formal definition. And a formal definition that doesn't make sense is kind of an odd thing for everyone to be latching onto. But at the same time, referential transparency is an extremely important thing. And I would personally argue that a language that has referential transparency is strictly better than a language that doesn't. So how do I, as the mechanistic reductivist, reconcile these two points of view? And there is a reconciliation. It's in fact that referential transparency is the single right strategy. That is, in other words, referential transparency is almost inseparable from the concept of immutability, which immutability itself is simply right once. But of course, immutable values still have to be stored in memory. There's still things happening, but a particular kind of thing. And what single right is a dependency elimination strategy. you can't generate race conditions with referentially transparent values because race conditions in CS are conflicts with writes. And since you can only write once and you can never read it before it's written, there's no possibility of a race condition. So, what then should we do with mutable state? This is the thing that's always a little vexing about a lot of discussion of functional programming. It always seems like, as long as you're in referential transparency land, everything is great. The moment that you step outside, all bets are off. But if you recast these all as dependency problems, then you don't necessarily have to throw up all bets. So, to restate our problem, in discrete time, order is not defined below your temporal resolution. And that's how we get race conditions. Now, typically then, if you have a straight imperative program that lacks function calls, some sort of like very simplistic assembly language, then you also won't get race conditions because your temporal resolution is at the order of single instructions. And single instructions will do a single thing, so you'll never get thrown off by them. But we tend to get problems when we get into more sophisticated languages. For example, if you have some blob of mutable state like an object that you then pass to a function, and the function mutates it without your knowledge, then you do, conceptually speaking, get a race condition when you read it later, because you weren't expecting a write to your state. So the write that you didn't expect is racing with the read that you did. A more obvious example of this in serial programming is when you have event systems like in GUIs. And oftentimes you will set up chains of callbacks and then immediately lose track of them. And then the order in which the event system decides to dispatch the callbacks is going to determine how race conditions get resolved. But that's really not a good answer. And then, of course, we also get this with parallel programming where the effective temporal resolution is some sort of like weird thing that scales based on how much you care about any particular string of instructions. So, if we pose things in dependency terms, then a race condition is a diamond subgraph in the dependency graph. In this case, what I mean by this notation is that the blocks are events that are occurring, and the arrows indicate a right direction, as in event A triggers and it writes to B, which then triggers an event on B. Event A also writes to C, which triggers an event on C. And then B and C will both trigger events that write to D. So generally, the canonical race condition is when you have diamonds in writes. So the thing that I'm proposing doing, that I am in the process of doing, is to make a language where the syntax is isomorphic to the edges of the dependency graph. See, the classical problem with all of this stuff is that the computer engineering types, the large-scale parallel programming people who are really into this stuff, also have the problem that they're just married to C++. And you generally cannot do this with C++ because at the very least, pointer aliasing is going to kill you. So my proposal is to make a language in which the syntax embeds edges of the dependency graph. And the way that you do this is you have your fundamental statements be of a form where you have some kind of event, and then you have a block of code with any number of stateful reads and pure transformations. The reason that you can do that is because reads will never mutually conflict with each other. Reads are always safe as long as you don't have writes. So stateful reads and pure transforms as sort of a fundamental thing, even though this violates the classical notion of referential transparency, is still generally safe in the ways that we should care about the word safe, at least in my opinion. And then finally, we have a write target. For example, if you click on a button and then want to send a label to some value, then the event would be the button click, and let's say there's a text box and you just want to copy the text from the text box into the label. You would have an event, perform a stateful read on the text box, and then your write target is the label. And in that situation, you create a dependency edge from the button to the label, the button to the label and the text box to the label. That is, all stateful reads along with the event produce an edge directed towards the right target. So with that in place, the compiler should forbid diamond patterns, and if it does that, you should have a program that is conceptually free of race conditions. But as Haskell more or less demonstrates for us, this requires a language level implementation. If this were simply done as a library or framework, then you would also have tons of ability to just randomly violate the rules, much like trying to long monads onto F# has the problem that the F# compiler is not aware of monads, so you can always violate the monad assumptions. And then, also as with Haskell, style should adopt accordingly into a form that's simply not prone to producing race conditions. So now, that leads to the important questions. Is it too strict? That is, when I practiced taught this at Los Alamos with some people who were actually reviewing parallel programming, one of the questions that comes up is, do you ever need race conditions to write a program? My suspicion is no. Well, my suspicion is kind of, which I'll get back to in a second. For ordinary things, if you have an event callback system already in place, then it should be the case that you can eliminate edges. And the way you do that is by putting in buffers. That is some data structure which is written to and then collectively written to and then writes to that will fan back out. In general, what we like is hourglass patterns. That is a fan in and then a fan out. It's the opposite that's a problem, a fan out and a fan in. So if you focus your fanning in on a particular data structure and then allow it to fan back out, that does solve at least some problems. So then, as far as the case where you really have a problem is if you're writing the event system from scratch, you have a situation where you have an event coming in and you need to redispatch it to one target. For example, you click on a GUI, and if you're writing this at a very low level, you get a click event with coordinates, and you need to redirect it to the correct widget. In principle, that would represent an edge onto all widgets, which would then make everything race conditions. But in practice, that's not true because you're only ever dispatching one event at a time. So it ought to be safe in that case to eliminate edges. That is to make this sort of mutex operation, or sorry, mutex, the thing where you have an IC that has an incoming value that selects an outgoing signal. What are those called? Someone has to know this. Multiplexer. Right. So multiplexing would probably have to be a fundamental data structure in this sort of system. So there's a question, what other fundamental data structures would be necessary to hold everything together? When I say this is scalable, I mean that in terms of project size. This is a sort of global optimization on a computer program, and it's not entirely clear whether or not you can keep that together in the long run. One advantage is that this also gives you automatic dependency visualization, so it at least gives you some ideas to try to winnow it down and possibly with good enough project management keep it running. But I'm really not sure whether or not that's plausible or not. Ultimately what it comes down to is these feel like sort of experiential questions. That this is fairly virgin territory to my understanding. So it's hard to say, to make these sort of practical engineering judgments on it. So, as I said, we are working on a language, and in fact, well, hopefully having the language in place will allow us to be a little clearer about all of this. So, ultimately, I feel that if we pose the phrase race conditions broadly enough, that does in fact encompass most of the really major problems that come up with program design. And referential transparency does solve an awfully large amount of race conditions. For the rest, hopefully language level dependency analysis will work. We're still hoping to find out whether or not that's true. So now, as I said, I did not talk about the language that we're actually making at this point. That I will be talking about immediately after this in room D115, which is a complete departure from this talk, probably more technical, or if not that, at least more specific. Otherwise, that is the extent of this talk. Are there any questions? And I should note that since I need to walk my laptop set up over there, questions may be a little short. So yes, any questions? Yeah.
It doesn't sound like you're talking about data storage or databases specifically, but have you looked at Datomic and what are you solving a similar problem to what I trying to solve?
I'm not familiar with that, so you have to clarify.
Maybe I can talk more on it. But Datomic is a database that looks like it's trying to do some of these things.
Right, so yeah, this is at least supposed to be a general purpose programming language. You know, the original problem I had in mind, as I kind of alluded to throughout, is GUI design. You know, I was trying to make a GUI program, and I was realizing throughout that there's this just massive unsolved problem with just things going everywhere. And that spawned a project that then got out of control and resulted in creating a programming language.
That's all.
Yeah. Yes.
You may have said it in any of this, but what's a stateful read?
Well, right. So one example, the Haskell-ish example, would be having an IO ref. Then the read IO ref action is a stateful read. You know, in object-oriented languages, a stateful read is an accessor on some kind of stateful object. So then likewise, you know, a stateful write is a modifier write on IO ref or a mutator on an object. Yeah.
So when you talk about solving all these problems, are you talking with reference to operating system threads or just within the language? Would you need help from the operating system?
No, so, right, the parallelism stuff is sort of less thought out because it's not exactly my focus, but the general thought would be that a dependency graph also tells you all of the locking that you ever need to do to perform any particular operation. That is, in order to invoke any particular event, or rather resolve any event, you know, you potentially need to do locking to carry that through. And the problem with locking is always deadlock, the Dining philosopher's problem. So the biggest thing a dependency graph does for you in that particular situation is let you know the topology of the locks, and then you can choose various locking strategies, but it does give you a starting point for deciding on how you want to lock. Additionally, you know, in terms of the state stomping sort of stuff, where you have like a button that forks events and then they converge back at some point, and what gets written at the convergent point is based on, you know, either the dynamics of the event system or the dynamics of the parallel thread execution. It would also prevent that. But ultimately, state stomping is what this is really about. Any other questions? Yeah.
So, with your language, so say, could they still cause race conditions in your language, or are you going to completely eliminate it so that if you analyze the graph basically and see that they have a diamond subgraph, you're going to basically say, no, we can't do this?
Right. And also say which edges are.
Right, yeah.
Or which paths, right?
Right.
Yeah. Yeah, no, this is more of the Haskell view of things, that you go for safety, and people just have to adapt. I mean, ultimately, part of what motivated a lot of this is one of the lessons that you can take away from Haskell is that we're very clever, but in the sorts of third-order abstractions involved with language design, we're maybe less clever. So it's usually better to impose restrictions at the language level in order to get theoretical benefits in the long run than it is to just say, oh yeah, you know, you figured it out, you're fine, you're a smart person. Okay, well, I think I'm going to go ahead and run over B115 if you feel like